Okay, it's 7:30 and we're going to get started. Welcome to the April meeting of the Johnson Space Center Astronomical Society. I'm Doug Holland, the president of the JSCAS, and this is our agenda for this evening. First, we're going to have Dr. Brandon Reddell with JSCAS and JSCs bring us our main presentation, Estimating the Age of the Universe from Globular Clusters. Then we'll have a DIY Astronomy with Chris Wells on dust mote diagnosis and sensor cleaning. That'll be followed by DIY Astronomy, more pi experiments with Treavor Quinn. And then we'll have David Haviland for the last three of our topics, a member's minute about a new nova in Sagittarius. David will be giving that for Paul Maley, who lives in Arizona now. And then there will be a member's minute update from the Georgia Observatory, and we'll wrap it all up with Star Party news. So first, we have Dr. Brandon Reddell, Estimating the Age of the Universe from Globular Clusters. I'd like to tell you a little bit about Brandon. Brandon is currently a member of the JSC Astronomical Society and works at NASA in the ISS Research and Integration Office. His background is in high energy physics, and he has worked space radiation environments and effects for various programs at JSC, and now helps researchers get their science completed on the ISS. He has been an amateur astronomer most of his life, and only recently has tried to tackle astrophotography, a rewarding hobby he enjoys working and discussing with other club members. With that, I'd like to turn it over to Dr. Brandon Reddell.
Brandon, your slide is ready. You have a go.
Okay. Well, thanks a lot, Doug, for the intro, and it's a pleasure to be back here today talking to the club. And as Doug said, I'm going to be talking about globular clusters and how we can use them to measure a lower limit to the age of the universe. So in my talk tonight, I'll first talk about HR diagrams. That's Hertzsprung-Russell diagrams. What you get from them, from the star magnitudes, the luminosity. And then I'll show a few examples from other HR diagrams from other clusters to kind of set the stage of why we and how we can estimate the age. And then I'll actually walk through an example. I'll first talk about how folks in academia do it using something called Isochrones. And then I'll use the cluster M12 tonight to really walk through what I call a simple process that as long as you have the right kind of filters, and this is actually a challenge maybe for somebody in the club like Doug or Chris or Treavor, I think it's something we can do through our telescopes that we have here in the club. So I'll walk through that example for globular cluster M12. And then I'll briefly mention some of the more complicated ways that are done using more sophisticated methods, and then kind of show a summary and a comparison at the very end. So first, let's look at HR diagrams. If you're not familiar with them, it's an easy way to put a lot of information about stars onto a single plot, and it's a graph that basically has temperature on the bottom, and the odd thing about it is increasing temperature goes from right to left, and then we have something called luminosity on the vertical axis. And so luminosity, typically it's plotted in relation to reference to our sun. So if a luminosity is 1, it has the same output as our sun. And luminosity, I'll talk a little bit more about that later, but it's basically the total energy output per unit time of a star. And when you look at all the stars in our galaxy and you plot them on this type of diagram, you'll see that they all line up on something called the main sequence, which is this main diagonal line through their main life cycle process. And as they, depending on the mass of the star, as they get towards the end of their lives, they kind of branch off into the upper right area where they become red giants or even supergiants. And then for even more massive stars that in a later stage of life can drop down and increase in temperature and decrease in size and become white dwarfs. So here's another example on the right side of an HR diagram. And what's different with this one, not only does it show, the general categories of stars in the main sequence line, you have these blue sort of tracks that kind of, depending on the mass of the star, it shows how during their aging cycle, after they begin their sort of the end of the life of their star, how they drift off of the main sequence. And so you'll notice stars in the upper left that are more massive, therefore have a more negative absolute magnitude. And I'll talk about what that negative means later. But you'll see that they kind of, when they branch off the main sequence, there's actually an intricate balance between the increase in size, which correlates to a decrease in temperature, but there's also a balance with the right luminosity. So it tends to be almost kind of like a horizontal line, and they call that the horizontal branch. Whereas stars like our sun will move upwards on this HR diagram and become a red giant near the end of its life. And so I want to keep that in mind, because I'll come back to use this chart later to help show how you can get the age and the distance to the globular cluster. And so what does the HR diagram tell us? So I mentioned luminosity. That's how much energy is released from the star per unit time. And it's related to what we call the absolute magnitude. And again, I'm going to talk about this on the next slide, but it's basically how bright it is from a certain location. And then there's something called the spectral class. And that depends on the temperature. So we already mentioned that the temperature is on the horizontal axis. In this particular HR diagram, the temperature's on the top of the scale. And then there's something called the BV index. And that's really going to be the core of this talk, is understanding what the apparent magnitude is when looking through a B class filter versus a V class filter. And we'll go into all that gory detail, but this BV index is directly related to the temperature. And so what do you actually get from magnitude and luminosity? Well, first of all, there's two types of magnitude. There's the little m, which we call apparent magnitude. And that's basically a measure of the luminosity, or you can think of it as the brightness of the star as measured from Earth, right, from here. Whereas the absolute magnitude, capital M, that's the apparent magnitude that you would see from the star if you're 10 parsecs away from it. And so a parsec is a measure of distance. It's basically 32.6 light years. So it's more of a reference distance from a star. And so to give you an idea, in case you didn't know about magnitudes, the higher the number, the dimmer the star. So bright objects like Jupiter, Venus, the moon, the sun, they all can have actually negative values. And so and it's sort of like a logarithmic scale. For each delta between a magnitude, there's a factor of 2.512. So what that means is a magnitude of 2 is about 2.5 times dimmer, because it's larger than a magnitude 1 star. And so the idea is, if you know both m, little m, and big M, apparent and absolute, you can calculate the actual distance to the star. And that's through this thing called the distance modulus, which is just the difference in the apparent and absolute magnitudes. So it's equal to 5 times log of the distance, so -5. So you can actually re-engineer that equation and solve for the distance, as long as you know the two magnitudes. The other important piece of information is the luminosity, which we said is the total energy output of a star. It's related to the mass, and it goes as the mass to the 3.5 power. You'll see that a lot in astronomy textbooks. It's not exact, it's more of an empirical relationship, but if you think about it, the more massive a star is, the more quickly it uses its fuel, so the lower its lifetime, and the hotter the temperatures can get on it too. And so that's why we see a lot of the massive stars are blue stars. And so you can use these relationships and solve for this, what I call the life expectancy, T. If you think about it, it's just the amount of fuel divided by the rate of consumption. And so using these formulas, if you took the mass of the star and you divided it by the luminosity, which is mass to the 3.5. You can solve for it. You get this relationship. It's basically 1 over the luminosity raised to the 0.7143 power. And so we'll use that formula at the end to estimate the life expectancy. And I do want to, yes.
We have a question for you.
Yeah, sure.
When you had the formula up where it had in reference to distance, is the distance in that equation in parsecs or light year?
Yeah, that's a good question. It's in parsecs.
Okay.
Yeah.
And one other for life expectancy, what is considered the end of life of the star?
So, yeah, okay, so because the HR diagram is all based on the way they're constructed is basically in reference to our sun. So in this particular case, because luminosity is in units of stellar units, everything's based off that. So, and that's what that last note is. It's based off basically that our sun has a 10 billion year lifetime given the type of star that it is. And so that's sort of the reference point. So just keep in mind, I mean, these aren't all exact numbers, right? There could be small variations, but it's only in percents, right? So when you're talking a percent or two out of, 10 billion years or so, it's that's kind of in the noise in terms of astronomy, but everything's relative to our sun. Hopefully that answered the question. Okay, so, and if it didn't answer the question, we can talk more about it at the end. So why do we study globular clusters? Well, first of all, we know that they're some of the oldest objects in our galaxy. Another unique feature is that given the relative distances, the cluster itself is basically all about the same. All the stars in there are about the same distance from the Earth, assuming you neglect the depth of the cluster. And on a large scale, when you're talking thousands of parsecs, that's pretty small. And then, all the stars are the same absolute age because the cluster developed at the same time. The only difference, like if you look at these pictures, the difference in colors, which tells you a little bit about the difference in the temperature and the life cycle of the star. These differences are only attributable based on their fuel consumption or their mass or their size. And then all the stars in the clusters were formed out of the same interstellar clouds, so they basically had the same chemical properties. So backing up just a little bit, you can see a lot of these diagrams on the internet, but what I wanted to point out is when you kind of look at the universe as a whole, so there's an active area of astronomy trying to understand when were the first stars and first galaxies, and it is generally accepted the first stars formed several 100,000 years after the Big Bang event. This particular chart shows 400,000 years. There's a couple other ideas that have it a little bit earlier than that, and then I'm sorry, a couple 100 million years. I said thousand, a couple 100 million years. Whereas the first galaxies were close to 1 billion years. I think one of the latest papers has one around 800 million years or so. We know they can't start earlier than that because the elements weren't around. It took so many, let's say, thousands to millions of years to just produce enough elements where you can have the gas clouds to form the stars. So we know that if we can measure, get a good distance on some of these earliest stars, given our Big Bang cosmological models, we can have a good guess on what the age of the universe is. And it's not perfect, but it's an estimate.
Brandon?
Yes.
Is that expansion from the Big Bang spherical in nature? Like it's going out from all directions?
Yeah, that's the big question. So spherical, when you talk about spherical, right, you're assuming a three-dimensional universe, right? So the structure of our universe is really more than that because it bounds our three-dimensional universe. So there's models like in string theory that predict up to 10 dimensions, but only 3 of them are expanding. But the idea is you have a central point and it's expanding in all directions, right? And there could be more than 3. The 2D and 3D analogy is if you think of a balloon, the center of the universe would be kind of like at the center of the balloon, but our universe would be the surface, right? So since we live on the surface of a balloon in this example, you have no way to measure where the center is because you can't see out of the surface. And likewise, going up a dimension or 2, that's the way our universe is. We don't know where the center is. We just know we're expanding. But it's expanding from equally in all directions from wherever it started from. That's very hard to visualize too. So moving on, and feel free to ask questions. So I just want to throw a couple examples. So this is the HR diagram of Globular Cluster NGC 362. I just picked some of the ones that look kind of nice, but as you see, you'll see the on this plot here, you have the visual. So this is the apparent magnitude through an F606 filter, which I believe is a V filter, or the visual. And I'll talk about what that means in a minute, versus the B minus V index here. And so what you notice is, the stars seem to follow what looks like a main sequence, and then there's a bend off from that. And then there's this blue line that goes through it. And you can actually model those things, and that's what is called an isochrone. And I'll talk a little bit about that. Here's the Omega Centauri. This is a great globular cluster that we can actually see when we're out in West Texas. It's usually pretty low on the horizon. It's got a couple million stars all clumped together. It's quite beautiful. You can actually see it with your naked eye. And so, again, it has a similar type plot. Now, if you notice from the previous and the next view, the vertical scale changes on all these, but they all have a general trend. And then this is the great cluster in Hercules, M13. So it's very similar. And then I kind of searched around. I was trying to find the youngest cluster that we know or that we have data on. And so I found this one called Whiting 1, and I'm actually not sure where it is, but it came from the Sloan Digital Sky Survey. And it's estimated that this one is only 5 billion years old. So there's not a whole lot of data here. And you can see here through the visual filter, we're down at magnitude 20 to 24, 22 to 24. So it's a lot dimmer than some of the other ones. And that's indicative because it's a very young and distant cluster. So I mentioned isochrones. So again, here we have the HR diagram, luminosity versus temperature. And basically what an isochrone is, it's a theoretical calculation of basically of an aging star population. And they call them stellar isochrones. And basically what they represent are just connecting the points relating to the same time or equal times of the stars in various phases of their in their life cycle. And so what you see is they all, depending on the age, that's the color of this chart here, they all fall along the main sequence. And you'll see the youngest stars up top, the blue curve, start peeling off this main vertical diagonal line horizontally first, and then after about 20 million years, you see it dropping down some. And so as you go in time, you're coming down the main sequence from the upper left to the lower right. And so the further down you go, basically, the older the cluster. And so the key thing here is if you can identify where this bend is I'm not sure if you can see my cursor, but I'm looking at the red curve. Where it leaves the main sequence and bends off, that's called the turning point, and that's an indicator of the age of that particular cluster. So one other piece of information we need to know is, so I've been mentioning filters. So this graph here is a plot of, it's called a Blackbody curve. Okay, any hot object has a curve like this, and it's just a plot of the intensity of the light emitted from the object versus wavelength or frequency. In this case, We're talking about wavelength here. And just like your oven, right? If you heat up an oven to 400 degrees and you could measure all the light spectrum coming out of it, it would have a curve similar to this. And it just, depending on where the peak is tells you information about the temperature of the object. And so we know hotter stars put out more energy in the ultraviolet and the blue wavelengths, and medium temperature stars tend to put out most of their energy in the visual wavelengths, which are the mid-range. And then the cooler stars, like the reddish ones, put most of their energy out in the red and infrared regions. So what that tells us is the lower the magnitude, like I mentioned earlier, the lower the magnitude, the brighter the star. So it's more bright through B and V filters for lower magnitude stars because they're higher energy. And so what that tells you is if you could look at a star through a B filter and then through a V filter, measure the apparent magnitude called MB, and then measure the apparent magnitude through a visual filter. As I mentioned before, that's called the color index, and that'll give us information about the spectral class of the star, right? Because those other HR diagrams I just showed had a horizontal axis that was B minus V, and that's related to temperature. And that tells you your horizontal position on the HR diagram. And just real quick, here's what the filters look like. They would just screw onto your eyepieces or your camera lenses. And what's shown here on the graph is just the U, B, and V filters. And so we're primarily concerned right now with B and V. And what this graph is showing is the percent transmission versus wavelength in nanometers. And so what it's telling you, if you look at the B, this is allowing light with only wavelengths from about 390 up to about 510 or so nanometers come through. Whereas the visual filter, the V filter, it's allowing a little bit higher wavelength light, peaking around 550 nanometers to come through. So it's kind of like you're only observing part of the spectrum on each one. So let's walk through an example for M12. First of all, if you look at the pictures on the right, M12 through all wavelengths looks like the top right image. So that's showing all frequencies of light like you would through a full image with no filters. And then the bottom two pictures are showing what it looks like. And it's actually kind of a segment of it, just so you can get some contrast between the black background and the stars. But as you might expect, there's not a big difference between the V filter and the B filter. But there is a difference. And so here's the process. So first you would just use an astrophotography. You would go off and you would, through using each filter, image M12, as long as you need to gather good data. And when you do that, you can either, hopefully there's a reference star that's not part of the cluster, but it's in your field of view, or you could just go to a separate star, because you will need a reference star to kind of calibrate your software and your processing. And so what you do to do that is you can go to the website like I have here. There's many of them out there, and there's some softwares that do it too. But if you have if you know the star that you're looking at, you can find it on a star map by aligning up the stars in your image to a star map. You can find a conversion factor by looking up what the magnitude of the star is versus what your counts are. Your camera software can tell you how many photons basically are being counted from that reference star, and so you can get a conversion factor from that. So then once you have that, then you start sort of a painstaking process to identify as many stars as you can in the cluster, and for each image, using your B filter and V filter, you can compute the visual magnitudes for each star. Now you don't have to do them all. You just want to get as many as you can, over as big as range as you can. And then once you have those two numbers, you can subtract the two to get the B minus V index. And so that's what this would look like. For M12, now I didn't actually do this. I actually found some data on the internet. So I put the data in Excel, and so that's what the left big white box is. Okay, so the column A is just showing my apparent magnitude through the B filter, and then column B is the apparent magnitude through the V filter. C is just the difference between the two, and then D is just a copy of B again, so that I can make this plot on the right. And so this is the HR diagram that if I would have taken that image, just plotting the B minus V index versus the visual magnitude, it kind of looks like an HR diagram, right? It's showing, I have it different kind of scales here, so it's a little bit squished, but you see a main sequence and then a turnoff point. So the next step is you have to do a couple corrections. If you look at the image to the right, this is just showing more like a wide field view, showing kind of looking at our galaxy, and there's various clusters, pointed out here. But the point is when we're looking at most of the globular clusters in our galaxy, a lot of them are in the disk region, and so you have to correct for something that's called extinction. Because of all that dust, the light coming from that cluster, just like at sunset, we see a reddish sky near the horizon, and it's more blue up high. Blue light scatters more easy than red light. So what happens is that the frequencies, the wavelengths that we observe through the filters, or even visually without a filter, tend to be redshifted a little bit. Now, it's not redshifted like a Doppler effect, but they call that extinction. It's actually called reddening, and then there's extinction, which includes the decrease in brightness. So you have to correct for that. And so there's a correction curve. I just use this one I found on Wikipedia. And since I'm using the visual index, it's a function of the wavelength. So based on your wavelength, you go up here and you can get the correction factor. And I'll show you how I applied that here in a minute. The second correction that you have to do is for the atmosphere. Now, it's a little bit weaker of a correction, and it kind of depends on the angle. So for this particular calculation, really, since it was just an exercise, I just assume we're looking straight through the zenith direction, straight up. So that's the minimum air mass thickness. And also used a plot from Kitt Peak, right? So that's not quite the same thing as here in Houston, but ultimately it's not going to make a big difference considering the other error bars from estimating on the graph. So, but depending on the wavelength of the filter that you're using, so I'm using 550, I can go up here and read off an atmospheric correction factor of about 0.15. And so that's subtracted off, right? If you think about it, if the atmosphere is distorting and blocking some of the light, we need the magnitude is actually a little bit bigger than what we're seeing if we're above the atmosphere. And so applying those corrections, you can replot the BV index. And so the original plot was just the blue points, and I had 0.7 for correction for the extinction, and then another 0.15 or so. So it was almost an order of magnitude, but it's decreasing it, so it's making it brighter, right? So that if we didn't have the dust and all that, this is what we would see from Earth, right? A little bit brighter.
Brandon?
Yeah.
We have a question.
Go ahead.
If we can determine the relative age of the universe using globular clusters, can anything be said or used from the stars in open clusters?
Yeah, you can do this. You can try the same process with open clusters. But the problem with open clusters is that they're typically younger than the globulars, and they're more spread out and different metallicities and things like that. So they're not the ideal clusters, chiefly because they're younger. So you're not going to get the older ages from the same thing from open clusters. That's a good question.
We have another question. The correction factor is the same no matter where you are in the galaxy, no matter where in the galaxy the globular is located?
Well, yeah, no, it actually, there's kind of a rule of thumb. I believe it's 1.8 magnitudes per kiloparsec is a general rule of thumb, but it does vary. To do this the right way, you'd have to kind of go to the research tables and actually look to see how far off the ecliptic plane you are. So it does vary a little bit, depending if you're looking straight down the ecliptic, like towards the core of the core of the galaxy, versus a cluster that's quite far off the disk. So there could be some differences there. Okay. So here's where we do the magic. So if you were doing this the right way, there's actually, and this is what graduate students do, you actually have programs that have good models for stellar processes depending on their mass and other properties, and you can actually model the isochrone for that type of star, and then you'd have to do that for a bunch of stars, and you do your best fit of your isochrone to your data, and then that would tell you basically where you would fit on this HR diagram. But the simple way to do it, now again, this is approximate, is if I back up one chart, if I take that orange curve, right, that's my corrected curve. Okay, first of all, so what I did, what you'll see in the next plot is I took 7 orders of magnitude, so for apparent magnitude of 14 down to 20, and then I used from 0.4 to 1. So I kind of shrunk it down just to capture most of the orange box. And so what you want to do is 3 orders of magnitude on the apparent scale will be the same. Well, it would also be 3 orders of magnitude on the absolute magnitude scale. And so what you want to do is shrink. So these green, hopefully you can see it, but the green points in the middle are my orange curve. That's my HR diagram. And so what I tried to do was fit the main sequence on somewhere on the the actual main sequence. But at the same time, I have to match up my B minus V index and my 3 orders of magnitude on the apparent and absolute magnitude. And so I actually had to do it in a different program where I could blow it up more. It's too hard to show here, but this is just a rough estimate, but it's fairly approximate. And so doing that, if you get everything lined up perfectly, then this will tell you your approximate turnoff point, your luminosity, and temperature, and all these things. And so the first thing was, so this chart, even though I'm talking about the age, I do wanted to show you how you can actually calculate the distance. So if you remember that distance formula, you need to have the distance modulus. So you need both M and M. And so for this particular diagram, I kind of looked at the point here at this elbow here, and between my apparent magnitude and my absolute magnitude, it's about 13.4 units. And so solving that formula I had back on one of the first slides for the distance, if you solve it for distance, it's 10 raised to the power of your distance modulus plus 5, all of that divided by 5, and then you raise that. And so when you plug in 13.4 for M minus M, you'll get 10 to the 3.68 power, and you do the math there, and it comes out to 4,786 parsecs. And again, a parsec is 3.26 light years, so that will come out around 15,600 light years. And if you go and look it up on Wikipedia, and there's other sources, there's variations, but I was actually surprised at how close it came from eyeballing that. Wikipedia said is about 4,800 parsecs. So it actually worked out fairly good on this one. I tried a couple other ones that I found data on, and usually, if you're within, I'd say 1,000 1,000 light years, that's probably kind of the limits I would say you can do on this particular method. Okay, so in order to do the age of the universe, you have to do this thing. It's called a bolometric correction. So if you remember, we only considered the visual magnitude, right? So that was a limited range, right? It peaked at 550 nanometers and it cut off all the other frequencies. But in reality, the star is emitting energy because it's a black body at all frequencies. So you have to account for all that extra energy loss. And so that's what's called a bolometric correction. And that depends on the type of star. Now, I happen to find on this particular website these correction factors based on the star type. And so identifying the star, actually, I explain it here in the next chart. But I'll go ahead and tell you here, it was around a G0, G2 type star around the turn point. So it has a small correction factor. Now, if I was doing a younger one, I could be up a lot higher. So it'd be more significant. But in this particular case, kind of got lucky that it wasn't a huge factor. But here's what I did. Based on that turning point, I'm looking at the third bullet here. That's the formula. Your bolometric magnitude is just your visual magnitude plus the correction factor. And so from that last HR diagram, my absolute magnitude was around 5.3 at the turnoff point. And looking up vertically onto the temperature, that corresponds to about 5,800 degrees Kelvin, and that equates to about a G2 star. So I looked up on that bolometric correction, and it's applied a minus 0.05 magnitude, making it a little bit brighter. So the visual magnitude, accounting for all frequencies, is about 5.25 in absolute magnitude. And then so once you have that, excuse me, so at the turning point, if you look on the far right side where the absolute magnitude is about 5.25, I can move all the way over to read to what the luminosity corresponds to. And at 5.25, it's around 0.75 in luminosity. So that's 0.75 times in solar units. And so using the formula I gave on the first or second slide there, to calculate the life expectancy or the age, 1 over L raised to the 0.743 gives you 1.23. And so that's in terms of solar years. So multiply that by 10 to the 10, you get 12.3 billion years. And looking up on Wikipedia, M12's quoted as 12.67. So I felt pretty good. I was pretty close. Now, I didn't pick M12 because I thought it was the oldest cluster. I just really was getting one that had data on it. But if you measure your own and search for your own clusters, or you can actually try to find the oldest ones yourselves. Just for comparison, I picked some other clusters. M2's fairly old cluster, and it's quoted as being about 13 billion years old. You remember we said the universe is about 13.7 or 13.8 billion years. So real quick, just to compare how well this method might be, if you look at more complex methods like using the cosmic microwave background, so this plot is kind of like a spherical plot of the history of our universe. So we're kind of like at the center, and we're looking out, and the further you look, the further you're looking back at time, and you can go only so far back to where you see this cosmic microwave background, and that's what this blue and green shaded region is. That's just the average temperature of the universe in any direction you look. And so we've had 3 satellites since 1990 or so: the COBE satellite, WMAP, and Planck. And there's even ground-based measurements now too, but as technology got better, we got finer and finer resolution. And so to make a long story short here, I'm showing some crazy math here, but if any of you remember some of your math, you can take any function and break it up into a bunch of sines and cosines, and it's kind of like a series expansion, and you can recoup your function. And the reason why we do this is you can break your function down into a lot of sines and cosines and then invert it to get your amplitudes. And it's related to what we call Fourier transforms and things like that. But what that allows you to do is produce something called a power spectrum. And that's essentially just a plot of your amplitude squared of all these sines and cosines. Likewise, if we're looking at a three-dimensional view of the cosmic microwave background, like this temperature variation, anything that's in 3 dimensions on a sphere that you're trying to map, you can do the same math that we just did on the last page, but they call that now spherical harmonics. And so it looks pretty formidable mathematics here. They're just a bunch of math functions. But again, you have in the middle here this amplitude function. And so use this amplitude to derive your power spectrum. And so if you look at small angular scales, large angular scales, that's the lower number, L equals 2. You get certain colors, but as you increase the angular scale, you get finer and finer. Just think you get more and more sines and cosines that map these, and you're trying to match this function here, this thermal map. And so that's what they do. They fit models and they use spherical harmonics, and then you have a good model for the cosmic microwave background. And so what they do is they produce this power spectrum here, and basically all these little bumps in the power spectrum of the cosmic microwave background, they have physical meaning to properties of our universe, like the density of the universe, how much dark matter, the Hubble expansion constant, and things like that. So what from the Planck data, that's probably the best known data from satellite data from their 2018 results. Here's an actual plot from their paper, just showing you the power spectrum. It looks real sharp here because it's not logarithmic scale, but it has a similar plot as the last thing I showed you. And finally, what they do is the standard model of cosmology is called the Lambda cold dark matter module, Lambda CDM. And it's the best known model because it produces the large scale structure of the universe, the distribution of galaxies, the right abundance of hydrogen, helium, which is most of the elements of the universe, the acceleration of the universe, given the amount of dark energy and dark matter and all these kinds of things, right? These are all assumptions, but it's a simple model. I shouldn't say it's simple, but it's simple in the sense that it only requires 6 input parameters, and then it can produce all these other ones. And so, so you can adjust the age of the universe. And what you do is you run this model, and then you compare it to the cosmic microwave background data. And then if it's off, you adjust all the parameters and you rerun it. And so you repeat this, and you do the best fit to the data. And oftentimes folks like to look at the Hubble parameter, which is the expansion rate, how fast the universe is expanding. If you actually look on Wikipedia, you'll see this is just like the last 8 or 10 measurements, but there's several pages of measurements, and it all ranges in this number around 71 kilometers per second per parsec. And the reason why I'm showing that is one way to estimate the age of the universe is from these best fits of all these models. Now, some of these are using the cosmic microwave background, but there's other things, other models using gravitational waves and white dwarf calculations and some other methods. But they all seem to average around 71 kilometers per second per parsec. And so that's, if you just imagine drawing a horizontal line through all these methods here, that you'll see that the CMB methods are a little lower compared to some of the other methods that are higher at 73 versus 67. And when you do this, if you just use the average, well, the age of the universe is 1 over Hubble's parameter. And so what this white box is showing here is just kind of like a units conversion. And if you use 71 kilometers per second per megaparsec, plug in all the numbers and, how many light years in a parsec, how many millions of parsecs, in a parsec, and kilometers in a year and a light year and so forth, you'll get 4.34 times 10 to the 17 seconds. Convert that to years, that's 13.8 billion years. And so, as you can see from this last plot here, there's a lot of competing models that, even though the average gives 13.8, depending on which model you use, you could be anywhere from, let's say 12 point something up to 14 point something billion years. And they're all within these huge error bars. And then finally, this is, I think, my last chart. I'm putting it all on one chart. How do globular cluster ages compare with everything else? So this vertical line through the center is kind of the average based on the Planck data that I showed earlier, around 13.8 billion years. The bottom two, the blue and the red bar, are what we get from globular clusters. So for really the last 20 years or so, there's been all sorts of studies done on numerous globular clusters that range, telling us 12 to 14 billion years. This Valsin et al. Paper 2020 is an interesting paper if you're want to read some more about that. But they calculate based on 60-something globular clusters that the average of the oldest ones is about 13.2 billion years old, and combining that with the age of the the beginning of the universe and models for how much time it took for the first stars to form, they calculate 13.5 billion years as an estimate from just globular clusters alone. So that compares quite well with other techniques, but as you can see, there's a lot of variation still. So that's pretty much all I have. So in summary, it's possible to get a ballpark figure for the age of the universe just by using filters and looking at visual and blue and visual and violet light, right? The B filter. Look in literature, doing a little bit more rigorous analysis using isochrones and looking at some of the spectral lines. Most clusters are quoted as dating, based on the oldest ones, to about 13.2 billion years. There's a lot of other complicated ways to do it, including the Lambda ACDM model, and there's other techniques too, which we didn't talk about. But over the last two decades, there's the key focus now is really looking at the expansion rate, because that's critical in determining the age of the universe. And so that's where most of the focus is trying to measure Hubble's constant. And averaging all the models together, we're about 13.8 billion years. And that's all I have. So I can take questions or we can move on, Treavor. So I'm not sure what we want to do, but that's my last slide.
Okay, I think there's another question that came in differently. It says, this may be somewhat off topic, but if open clusters are newer than globulars, have open clusters not had enough time to form, or are they incomplete attempts to make globulars, or is there no relation whatsoever?
To be honest, I think there's a lot of factors. I don't think open clusters are like failed globular clusters, because clusters are formed from very dense clouds. So less dense clouds, stars are more spread apart and, may appear more open. But, I'm not totally sure, but even the metallicity, which is the amount of elements heavier than hydrogen and helium, they're different types of stars in those, which is indicative of the the type of clouds that they form from. And so we just don't see, you know, I mean, there are new globular clusters, and there could be newer globular clusters that are just as young as some of the oldest open clusters. So it's actually a complicated answer. I probably don't know it, but it's not from failed globular clusters. That is a good question, though.
Okay. Back on your BV method, I understand how you got your apparent magnitude, small m, but not the absolute magnitude, big M.
Okay. I'm going to go back. Let's see here. I think you're talking about this chart. Okay, so big M, so you would do this for each star, okay? But really all you need to do is identify, actually, let me back up a little bit more. Okay, yeah, I guess this is the best plot to use. So really what you're doing is you're visually fitting your little m versus b minus v plot. That's what this green smudge is showing, basically. Now you have to scale. It's all about the scale. The b minus v is your horizontal axis, so you got to make sure that lines up exactly. And then on the horizontal axis, depending on how many orders of magnitude, you have to show the same orders of magnitude on that. And so as long as you can do that, then you can pick any star, and you know where based on if you draw a horizontal line through it, you'll know from your other plot what the apparent magnitude is, and for the same star on this plot, you can read the absolute magnitude. So it's just an approximation, right? It's not perfect because it's based on graphical interpolation. The real way, the better way to do it is to use computer simulations to calculate your isochrones and look at it that way. So I'm not sure if that answered it, but it's all about scaling the plot onto the HR diagram.
Okay, it looks like we've got a couple more. One, doesn't the 1 over h assume constant expansion rate?
Yeah. There's actually more complicated. So I didn't want to get into that, but that's true. It actually, there's more to it than that. There's something called the flatness of the universe. So that's one of the active parameters they're trying to measure. So it can vary anywhere from 1 over h to 2/3 over h. And so, but to do that to do it the right way, you want to calculate, because h isn't constant over. We know that the expansion actually decelerated for a while. I mean, it was always accelerating. It kind of dipped down a little bit, and then it's accelerating again. So ideally, you want to do it over multiple time steps, and then integrate, in time to do it that way. So that's really the best way to do it. And so for that, you'd have to know, and there's solutions to the general relativity. What the Lambda CD model is doing is it's actually solving the Friedmann Einstein equations with a lot of these assumptions for initial input parameters. And so you want to do that for a bunch of epochs and then integrate it over the life of the universe.
Okay. Are globular clusters older than the galaxy they are in? And how are they created?
So no, they're not older than the galaxy. So they kind of form along with the galaxy, and then not exactly, like, I don't know how you define the start of a galaxy, but basically what happens is you could already have a galaxy formed, and then you have this dense cloud of material, and it just takes some random perturbation on this cloud to cause the cloud to collapse. And then once that happens, then stars start forming, and then get more mass and causing more formation, and therefore, depending on how big the cloud is and how the stars settle out, you have a globular cluster. I think you see when you look in galaxies and other galaxies, when they look in the spiral arms, oftentimes stars pass, or these clouds passing around on spiral arms. You can get perturbations that way to create globular clusters. That's how some of the new ones are created.
All right. Thank you, Brandon. I think that's all the questions.
Okay. Well, thank you.
Back to you, Doug.
Okay, Brandon, thank you for that presentation. That was very interesting, and that sounds very intriguing. I'll have to get some B and V filters so we can see if we might be able to do that ourselves. Next up, we have a DIY astronomy, dust mote diagnosis, and sensor cleaning with Chris Wells. Take it away, Chris.
Chris, you have a go.
Okay, good evening. My name is Chris Wells. I'm now for something very different, talking about dust motes on your sensor, on your cameras that take all these wonderful pictures of globular clusters. So this is a DIY segment, and it's kind of a difficult yes-no decision whenever you do DIY on your equipment. So I'll take you through my thought process, and there is a happy ending. I promise you a happy ending at the end. So there we go. So I actually bought a camera. It was an Attic 460EX. It's one of these, it's a CCD camera. And I bought it about a year and a half ago. I bought it used, and it was hardly ever used. It was practically new. And I actually did a first light image. And this is my first light image I took of this cooled CCD camera. And I took it indoors making it into a pinhole camera just by using a piece of foil and a little pinprick in the center. Now, this is actually a picture of my bookcase. But if you look at the picture, and you see a lot of dark little spots everywhere. And I didn't really know what they were. Now, there are no optics in this picture. Sorry, there's no optics in the train here, so you can't blame it on dust on the refractor telescope or the telescope you have, because there isn't any. It's a pinhole camera. And when I put my biggest magnifying glass on it, I actually got a sense of seeing some of the little dots actually on the sensor itself, if you catch the light just right. So I did know that the camera I'd bought used, it hadn't been abused or anything. I think it just came this way from the factory, or something had got dislodged in transport perhaps, actually had spots on it. And then there comes the difficult decision. What do you do about it? What do you do about it? You can't send it back. It's not that sort of thing. So I'd forgotten about this, but this was my very first light picture. I'd forgotten about the problem, and I started to use the camera, and I was getting really, really good results out of the camera. So I'd forgotten about the problem. And I was taking pictures like this, and this is a picture of the Iris Nebula. You don't see any of the dust. You don't see any of the spots on this picture. In fact, this is probably one of the best images I've ever taken. And so you start to ignore the problem, because the image processing techniques you use of taking flat frames and dividing the flat frame into the image frame of your stack actually gets rid of all the abnormalities caused by dust spots wherever they are in an optical train. So as long as you don't look at something and analyze it, it doesn't really become a problem, other than it's kind of a little irksome thinking you've just bought an almost new camera and you got some dust in the optic train there somewhere, or actually on the sensor. Here's another picture that I took of the Heart Nebula. As you say, even when you stretch these images with the right processing, you just don't see these artifacts. So a year and a half passes, and then I decide to go and use the camera on a different telescope at home instead of a West Texas site. And here's my picture just at home and you start to see these spots come back at you. And I did use flats, but I obviously didn't have very good flats. And in order to take a picture of what is Thor's helmet here, I actually had to do some really, really aggressive stretching. And some of these abnormalities did then start to appear in my image. And I knew I could probably get away with it still by taking even better flats than I already had. But then I started to relive that experience of, oh, there's a problem with my camera that I bought. And then you get the DIY decision. Yes or no? Is this something I really want to tackle or not? So before I did anything more, I wanted to do some diagnostics because I suspected, you know, when something's at the limit of your ability to see and you're using a magnifying glass, you don't really know where that dust is. Is it really on the sensor, or is it on the chamber itself, on the glass that separates the chamber from the glass covering of the sensor itself? So I really wanted to make sure and confirm before I'm going into the sensor chamber and doing an operation on what is an expensive camera. So a couple of things. I got some instructions from the Attic service people. They're actually in the UK. Awesome service. They give you really good instructions. And so I knew what to do. But I did want to just, first of all, diagnose it and make sure that if I'm going to do something, I'm going to fix it right. And I want to make sure that I know what I'm fixing. So the first thing is, when you do your own images, how large are those dust motes? Generally, if they're really, really small, like mine were, they're going to be very, very close to the sensor. They're going to be either on the sensor or on the glass casing. If they're even larger, then they tend to be in your optical train somewhere, perhaps on your field flattener or your reducer. And if they're larger still, then they tend to be on the optical elements of the telescope itself. One thing you can do is rotate the camera to see if the spots move relative to the orientation of the sensor itself. And if the spots don't move and they're in a fixed position, then it's going to be on the sensor as well. So that was my confirmation right there, that it was definitely on the sensor. Still didn't know whether it was on the glass of the sensor or the covering of the chamber. And then what I did is I did another pinhole camera daylight test, and just to confirm and make sure before I got my tools out and actually engage in this DIY yes/no decision. So this was the image I took. This was the one I took in August of 2019 when I first got the camera, and you see all the little spots around there. And this was the image that I took. This was actually my flat image that I took at the same time as I did the Thor's helmet picture that I took from Light Pollution Central here in New League City. And if you look carefully, you start to see the patterns that you see in August of 2019 that I believe were on the sensor are exactly the same patterns that you see on the flat image as well. So basically, there's dust on my sensor, and in this period of about a year and a half, it had not moved. So the DIY decision there is a definite yes, I'm going to do this. Oh, and here's my pinhole camera. Fine engineering that was.
Hey, Chris.
Yeah.
On your 2019 picture, is that your pet snake crawling up the bookcase?
I don't even know what that is, I have to say. That's an undiagnosed object. It is a UFO. There you go. But it could well be a snake if you want it to be. Okay, so here's my sensor. First thing I did was actually mark the marks, because you've got to take that retaining ring out. So I like to know how many turns of the retaining ring you actually take before you're releasing it out, just so that when you go back into the operation and you actually reassemble it, that you're not cross-threading it, that you're threading it the same number of times, because it is a sealed chamber unit. Now you have to make a tool. I made a tool out of PCV pipe, and I cut a little piece of metal there that fits directly in those two notches there that is covering the sensor. So I actually made this little tool here to do that. The instructions that Attic provided me alerted me to actually a really awesome, rather than use Q-tips, they actually have flat Q-tips these days that are designed specially for sensor cleaning on DLS cameras. And I just want to show you that picture there. I didn't have any though. I didn't have any, and I wanted to do it today. You know, I wanted to do it on the day that I had reserved. I think it was a Sunday. I wanted to do it and get this done. So I didn't actually order any of those, but I thought those would look like the awesome cleaning tool. So I'm going to be probably placing an order for some of those just in case I need it in the future. But as I've sort of shown in some of my DIY segments before, I tend to keep things in the garage, things that may come of use. So for those of you who have ever played a clarinet or a bass clarinet, here are two bass clarinet reeds. They were used by my son, not by myself. So, you know, just goes to show those are really good at spreading things like glue. But I kept them and I reused them by cutting some lint-free sensor cleaning tissue. And these are kind of 99.999% pure lint-free things. And I put them, and I actually made the equivalent of what you can buy in these special flat Q-tips. I also used a vacuum cleaner with a variable suction in order to get to really try and get some airflow going to remove particles that I'm moving as I do this. So that's the tools. And my workbench area looked like this. And I just got everything ready to go. The most, I think, important tool there was glasses, because you're really looking at something very, very small and I can't see it. And a big magnifying glass as well, dust blower, the vacuum cleaner was set to go. And then it's the time of the operation. I've decided the very important decision here. You've got a $2,000 camera. Am I going to operate on my camera? Okay. So the operation itself, you have to open it up. You remove this desiccant type tablet, and you're meant to bake it for 24 hours to make sure it rejuvenates and can take moisture out of the chamber for you. So I did the operation literally just by sliding those homemade cleaning swabs and lightly stroking it across the sensor itself. And then I reassembled everything. You put the rejuvenated desiccant back in place. You seal everything back up in the chamber. And then you're meant to wait 24 hours before you ever turn it on again, because you're waiting for it to acclimate and all the moisture to actually be sucked back into the lozenge type tablet there that I'm calling a desiccant tablet. And then you do a test image. Well, let me tell you, I did that and the test image was not good. I ended up having dots all over the place, and they were in different positions. So I clearly didn't do a good job first time round. So I revised my procedure, I reopened it, and I did it many, many times over. And then I took test images each time to actually do that. And that ended up being the final test. I got rid of all of that dust. I think there's a few residual spots still there, which is impossible to get rid of. But I think about 99.99% of them are gone. So really happy with the outcome. Is there a question?
Yeah. If you rotate the camera, why wouldn't the Motes move?
If you rotate the camera, the Motes will move relative to the actual sensor itself, because they were on the sensor. And so they would rotate, but when the image downloads, it always downloads with that same aspect ratio and that same orientation.
And what did you revise about your procedure?
I realized that I couldn't do this one time, that I couldn't see the dust on the sensor, even with my glasses and even with the magnifying glass. So the only way for me to really see whether I'd got all the dust was to turn the camera back on, put the pinhole camera together again, and take a picture. That's the only way that I could discern whether or not I'd got all the dust. So I kind of semi-reconstructed it in order to do that. I also did not turn on the calling device as well, the tech caller. And I did that probably about 5 times before I was happy with the result.
Did you not use any lens cleaning fluid?
I did use some. When I first did it, I said, I'm just going to be able to dust these off. And that was my first approach. I was proven wrong on that front. Nothing would move just with a light brush, or even the pads that I created when I dusted those lightly across the top. Those items that were on the sensor were firmly there, and they were not moving. So I had to use some cleaning solution. The instructions that I got from Attic, it's funny, whenever you get instructions from European companies, they tend to say, what you got to use is get something called optical wonder. Well, you can't buy optical wonder from any supplier in this country. I think there's some transport issues because of the chemicals that they use in that. So I couldn't get something called optical wonder. What I ended up using was a very light cleaner called Pure Sol, which is, and I just put a little dab on there. I literally wiped on, wiped off, wiped on, wiped off a number of times. I did it very lightly, and that did get rid of things in the end.
And that was directly on the sensor?
That was directly on the sensor. And I think there's glass in front of the sensor. I think they create the sensor and then they put a sheet on top of it. And I think it's the glass on top of the sensor. Anyways, it then came to test time. So I took this picture. There's only one picture. It's just processed in different ways. And I took this from home, League City. It's obviously M81, Bode's Nebula. And I was pleased with the result. I could really stretch the image. The flats didn't have those dust spots on, and I could stretch the image to a real extreme, bringing out the really faint dust lanes that were really only about the same signal as the background sky glow, actually. I really pushed it in the processing, and none of those spots appeared. So I was really pleased with the output. And I couldn't decide which image was more true color or not. Looping it back to actually the previous presentation, the real way to know whether you're doing true color or not is a calibration cycle called G2V images. So you basically take images of a G2V star, you know its color spectrum, you know what it is, and you're meant to calibrate your red, green, blue channels against it. Well, since I hadn't done that, I don't really know which one is a true color picture in that case. But no, real pleased with the result.
Thank you, Chris. Back to you, Doug.
Okay, Chris, thank you very much for that presentation. I've had that experience myself. I know how painful it is, and yeah, when I've done it, I've had to do it multiple times to get the sensor clean. So that is a tough thing. Thank you for sharing that with us. Okay, next up we have a DIY astronomy, more pi experiments with Treavor Quinn. So I'd like to hand it over to Treavor to tell us about what he's doing with his Raspberry Pi these days.
Thank you, Doug. Okay, so with the Raspberry Pi, the main thing is we're dealing with a true DIY computer system that's only about $100 with all the cases and everything that you have to add to it. And Raspberry Pi also came out with what they're calling their high quality camera, which is a 12 megapixel camera. And in this next slide here, here's the camera. It's actually a sensor module. It's not really a full camera. It's just a sensor module. You have to have software to actually be able to operate it. So this is what it looks like in this picture. There's the ribbon data cable coming off the bottom of it. I've actually got the cover on it in this picture. The next picture is where I've removed the cover, and now you can see the sensor down in the bottom that's exposed. And what I wanted to try and do with this is actually see if I could take, here's a backside of the circuit board of the camera. What I wanted to do is to take and see if I could take a picture, an astrophotography picture with this camera. So what I tried to do first is I got the adapter to fit the 1.25" diagonal on my scope. I got that all assembled, put it in there, and I was unable to achieve focus. So the next couple of hours messing around with this, trying to determine if I was, too far away or too close with the back focus. What it turned out was with this and the housing, I was too far back. So what we ended up doing, or here's the Raspberry Pi itself, but where it connects in with the ribbon cable. But what we ended up doing is we completely stripped the housing off of the camera. So it's just that circuit board with the sensor on it. No housing, no adapter to fit. And we ended up taping that to the diagonal on my scope. And when I say we, this was Chris and I doing this experiment. And the reason why I wanted to see if this was actually even feasible is Chris mentioned, those astrophotography cameras are rather expensive. You're talking about a couple of hundred on up to several thousand. And it's the same with DSLR cameras. You can start off at a couple of hundred and you can go up to a couple of thousand. It's just all on, how much you're willing to pay. But I wanted to see if I could do this inexpensively. So here's this experiment. And here's an up close where showing the tape. And what we ended up doing was we laid a layer of tape on the edge of the diagonal before we placed the sensor circuit board on it to try and insulate it a little bit. And that's kind of shown here. You can kind of see the tape on the diagonal sticking out by the ribbon cable there. So finally we get to trying to image. So this is just one of the I think I was doing 1 minute exposures at this point of M81, M82. The dark spots are they're dust somewhere on the diagonal close to the sensor itself. And then with that, I think I ended up with probably about an hour's worth of images. And this was my final result in trying to process that. So it's not anywhere near the quality of the image that you saw from Chris. But I thought, hey, okay, we'll see what it'll do. And this is what we came up with, or this is how it performed. Now, I don't know if it'll perform any differently in a dark sky site, but we'll have to figure that out at a later date. Next, in this, I wanted to take it to a different experiment where I wanted to take that Raspberry Pi camera and hook it just to a DSLR lens. Now, Chris had an adapter available, so I mounted it. I even put it on a bar to be put on my tracker, and I tested it during the day. I was getting pictures through it during the day. I took it outside at night, and I wasn't getting hardly anything. But here's where I've got it on a ball head mount, and then attached to my tracker. And what it turns out is that the shutter, when you disconnect this particular DSLR lens from a DSLR camera, it closes the shutter all the way down to a very small pinhole in the middle. So as long as there was plenty of light during the day, it would take a picture. But at night, it was too shut down and too dark. So the next step in this experiment is to get an adapter that will allow me to open that shutter back up to see if we can run that test like this. And then one other experiment that we're going to do with the Raspberry Pi later in the year in this Raspberry Pi camera is we want to test it on planetary imaging. So we'll take that and hook that up to Chris's Maxitov Cassegrain and try and run some planetary imaging through it and see what we end up with. And that's about all I have. I'm going to hand this back over to Doug. All right, Doug.
Okay, Trevor, I had a question. So what is your future plans for that project?
Well, I'm gonna try the camera with the ability to open the shutter on the DSLR lens. Yeah. And then we're gonna try using it as planetary camera.
Are you finding any better way to attach the Raspberry Pi to the telescope?
Not yet, no.
So it's going to be blue tape all the way. Huh?
Well, I may look at something along to see what I can do about that as well.
Okay.
I had a couple of ideas, but I'm not sure yet.
Okay. All right. Well, thank you very much for that presentation. Okay. So next up, we have a historic first for the Johnson Space Center Astronomical Society. We're going to have someone who's going to give us 3 topics in a row. David Haviland is going to tell us 3 things in a row, which I listed out during the agenda. And starting with David's going to do the new nova in Sagittarius for Paul Maley. And then 2 other topics after that. So hand it over to David.
Doug, give me a minute. I don't see David's presentation.
Oh, maybe David left.
No.
I hear him.
There, should be there.
Okay, David, you have a go.
Okay. Paul asked one of Doug or myself to show this, but he did this originally by email. Many of you might have even seen it. On March 18th, he received an alert of a nova that had been found in Cassiopeia, and he was actually able to photograph it around 8th magnitude, but there was no precise measurement taken. The slide here has the RA and deck, And if you go to his page, paulmaley.com, you can actually see the image, and I have it in a following slide. Image of the nova, and compared to a Sky Patrol photo, and I'll show that here. He figures it should be easy for us in JSCAS to follow the progress of this, as it's reasonably well positioned since Cassiopeia is circumpolar in the sky. But I was looking at it earlier tonight and found that it's kind of dipping low in the northern muck, but it's still there. It'll come up toward the summer. Now, if you look carefully, this is Paul's picture. This is the AAVSO picture, and it is upside down. So Paul has matched this to match his picture. So this arrow here is this one all the way over here. And that arrow is matching another arrow, and this one is matching the top arrow. The yellow arrow is actually pointing to the rough location of the nova. Well, I wasn't completely thrilled with this because I couldn't exactly figure out where in Cassiopeia it was, and I wasn't familiar with the AAVO sheets yet. So it turns out Sky and Telescope, and you're more than welcome to snag this website here. From Sky and Telescope, they had a bit more of the introduction I was looking for, because here's Cassiopeia, and it's way over here, right on the edge. It's right on the edge of being in Cepheus. So it's off to the side over there. Scroll down a little bit more, you can actually see, there you go, Brandon, globular, 52, bright star down here, which I didn't quite identify, and then this blob right here is the nova, and it's also within walking distance of the Bubble Nebula. So it's hoped that photographically we can monitor this over some time and see if it increases or drops off. Now, here again, you can come off of Cassiopeia and star hop to this magnitude star, both 4.9, hop over here, get over to this triangle, and then work your way over again to that base star, M52 up top, and the Bubble Nebula over here, and dive in for the nova. I thought it was kind of interesting to see that. This is the AAVSO picture. That helps it all. Here's the that one bright star here, M52 up top, and we've got the 3 or 4 main stars that kind of form a semi-line here you can use as a landmark and work and walk your way down here. And if you can get your camera roughly in the right direction, grab a picture of it. I would love to, except I have a large oak tree that completely obscures my northern sky, so I would actually have to leave the house and go someplace, maybe the George, to try to photograph this one. Okay, going to change gears. The George Observatory actually had a soft opening on March 19th and 20th, and then again on the 26th and 27th. They only sold 100 tickets online only. Initially, volunteers were there by invitation, and that wasn't to be selective. They had to be cognizant of COVID rules, and in order to run the scopes, we had to drive them through cameras and have those cameras tied to television monitors outside. That was the only way HMS would say, "Okay, guys, you can open." No one but operators are currently allowed inside the domes, so everything had to be shown on the screen. We could have people come up to the door and they can look at the scope, but they do not come in, unlike previous times. So there was no eyepiece viewing here. You can see Connie's sitting here. This is actually the West Dome, the C-14 that's in the West Dome on the Paramount, and we've got a laptop down here. COVID has actually, as we know, reduced the number in our volunteer corps, and now the corps was actually further reduced by those that can drive cameras. So we're in the process in all 3 domes trying to find people that can A, drive the scopes, B, are comfortable with camera, or they can get worked up to be comfortable driving a camera. It involves live stacking. The main scopes main cameras we've been using. Where'd my mouse go? There it is. Normally we would have the software go to the telescope, and we go straight out to the eyepieces. Well, it's not that simple anymore. We got to have the software go to the camera. The camera has to be operated through SharpCap, and then we have to turn around and put that onto the monitor. The ZWO ASI 294MC is pretty much the go-to camera, no pun intended, that they're using at the George. All three domes, through either donation or purchase, now has access to 294 cameras. So I just simply brought out my laptop and had the drivers put on it. Outside, this is what's going on here. Connie's giving a quick tour of an image of the moon that we'd taken, and this is how we have to do that. We have to keep groups physically separate, 6 feet apart, for the purpose of public safety. And as I said, it's a limited number of online sales per evening. Here is SharpCap, and with some wandering, we were actually able. This was without the effort of Joel Brewer of FBAC, this picture wouldn't have happened. But this is live stacked. Obviously, most of you mostly recognize that this is the Horsehead Nebula. We had to come down here and play with the live stacking options in SharpCap, and this glow is actually internal glow from inside the dome. So we have to work that out. I did not have a red screen cover for my laptop, and my laptop is basically illuminating the inside of the dome, which is where the part of this sky glow came from. M42 live stacked, not too bad. It was a series of about 30 or 40 10-second exposures. I can't complain. You can at least see the trapezium tucked here. You've got distinction of the 4 stars. And then again, Horsehead cropping up here. Moon that we'd taken one weekend, I gave a couple of tours of the moon. There are some features there. It turned out reasonably well. There are a lot of logistics we still have to work out. Since we've gone to daylight savings, the sun is setting later, so we're having to open up later. We're now running like 8 to 10. We have to still keep the crowds limited. We've got 2 setups for deck scopes. So there's 2 TV monitors and all that can be used for deck scopes, but anyone else has to bring their own monitors, and that's no trivial feat. So as I said, the number of volunteers are limited, as are the folks needed to put things in play until this gets resolved. While this is supposed to be a soft opening, the George is currently planning on expanding Saturday public outreach, and in fact, volunteers are being asked now every Saturday. Okay.
Hey, David.
Yep.
How are you getting the image signal from the laptop to the TV?
HDMI cable. You've got to have a computer or a laptop that takes the input from the camera via the camera's USB, and then most of the laptops or computers have HDMI cables, and
Okay.
they have 20-foot HDMI cables that we can run out the door.
Okay.
All right. On to the SP report. Star Party news. April. This is what I'm more used to doing. All right. March 11th through 13th, Fort McCavitt, as we know, had been unfortunately canceled. March 12th, we did have an event at the Hack Winery. We'll talk about that. May 2nd through 9, I as understand it, correct me if I'm got an error there, Doug, but I believe that is the West Texas Star Party. pruderanch.com. You can find out what's going on there. At the moment, the only thing we have on the docket are Hack Winery events, all the way out to September. Starting the next one will be tail end of next month in May. Hopefully, October 7th through 9, the club will be able to make the trip to Fort McCavitt. October 15th, we are still planning an all-clubs meeting. We do not have a speaker yet procured. October 16th, in light of what I've just told you about the George, Leonard and I are wondering about trying to hold a day. We're still thinking about it. We'll have to get with Kavita, the director of the George, and who's also the director of HMNS Sugarland, and figure out how we can do this and maybe have a limitation of 500 to 750 people. Try to man things at some level. And on the 19th, Friday, November 19th, we have the final hack event from 2021. To that end, we had an event on March 12th. We had approximately 100 guests: Keith Brandt, Treavor Quinn, Chris Wells, Chris Randall, Kevin Timmons, and Connie and I were there. It was a reasonably clear night despite the sky glow here. Chris brought that cute little Dob again that he managed to pick up, and short of it actually rotates. It's really kind of cute. I got Chris, Treavor, and myself here. Trevor's working on his iPad and his critter, and he's got that sitting here on the tripod that he just kind of got through talking about. Gentleman brought his Dob. There he is standing up. That's Keith Brandt. Here's Timmons. He brought a small SCT. M42 was there. A couple of other things were there. I believe Mars was out off in the western sky. And Chris Randall sweltering a little bit. It was kind of a sticky, humid night. And then Connie and I. And we're hoping things are starting to get up slowly. Right now, again, all we have on the calendar are hack events, as well as A-Day, and we'll just play it by ear and keep going. Keep hoping that 2021 is going to be a damn sight better than 2020. And as if no one was really surprised why he changed his name when you went from Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Doug, Neptune, Pluto. That's all. Back to you, Doug.
Doug, you have to go.
Okay, David. Haha. All righty. So that was it. And those 3 topics from David. This is the end of our meeting. Our next meeting will be May 14th. We will have the Challenges of Mars, a long series of circumstances with Leonard Ferguson and Annie Morgetts with FBEC. So thank you very much for attending our meeting, and hope you can join us next month.